Hey everyone, and welcome back. On behalf of Forge College, I am absolutely thrilled to be your guide today as we dive into a brand new explainer. So we're bridging straight from our previous lesson, from manual steps to scripted workflows, directly into the beating heart of the applied Solidity development track. You've already seen exactly how we can automate and script all those complex interactions on the blockchain. But today we're talking about authority. Specifically, we're going to look at one of the most fundamental, widely used, and, let's be honest, debated architectures in all of smart contract development, the ownable pattern. So let's just dive right into this and see how we can build a machine with a true master key.
Here's our quick roadmap for today's explainer. First, we'll meet the switchboard operator. Second, the mechanics of the pattern. Third, the root access risk. Fourth, the ownership lifecycle. Fifth, real-world trade-offs. And finally, number 6, wrapping up and next steps.
All right, let's kick things off with Section 1, Meet the Switchboard Operator, otherwise known as the Single Administrator Model.
So whenever you design a smart contract, you have to make a big decision. Who actually gets to push the big red buttons? I want you to imagine, just for a second, a legacy old-school on-premise server room. Sitting right in the middle of it is one solitary operator at a terminal holding undisputed root access to the entire system. That beautifully illustrates our core concept today. To quote our source material directly here, the owner is the contract's administrator or switchboard operator. Now, unlike multi-role setups that split responsibilities so no single person can accidentally bring down the ship, the ownable pattern kind of throws all that out the window. It goes all in on absolute simplicity, giving a single, exclusive account total control over the contract.
Moving right along to Section 2, Mechanics of the Pattern. Let's go ahead and pop the hood on this thing.
When you look at the engineering spec sheet for this pattern, it is beautifully compact. It really revolves around just 5 main features. First up, you have the owner variable. That just holds the single authorized address. Then there's the constructor, or an initializer, if you're using proxies. This typically sets that initial owner right at the moment of deployment, usually assigning it to the person deploying the contract, known as msg.sender. Next is the owner-only authorization modifier, which is essentially the bouncer at the door. And finally, we have 2 distinct lifecycle operations. There's transfer ownership, which lets you hand the key to someone else, and renounce ownership, which literally burns the key entirely by setting the owner to the 0 address.
Let's drill down into that middle component for just a second, the owner-only modifier. By definition, it's an authorization mechanism performing a runtime equality check between message.sender and the stored owner address, reverting if they don't match. Now, the reason this is so brilliant is that it deliberately decouples permission checks from your core business logic. Think about it. If you have a function that changes a critical fee rate, you really don't want 50 lines of complicated authorization code cluttering it up. You literally just tack owner only onto the function definition, and the modifier handles the whole shebang. It keeps your code incredibly clean and, honestly, super easy to audit. If we trace the exact mechanical steps the contract takes when an owner-gated function is called, it operates like a highly predictable 3-step machine. Step 1, read the state of the owner variable. Step 2, execute a dead simple equality check. It just asks, is the person calling this function, message.sender, the exact same address as our stored owner? Step 3, if the answer is no, boom, hard revert. The transaction crashes, access denied. But if the answer is yes, the doors swing open and you proceed with the privileged action. It's binary, it's fast, and it leaves absolutely 0 room for ambiguity.
That brings us to Section 3, the root access risk. What actually happens when keys go missing?
So I want you to ask yourself this kind of humorous but actually terrifying question. What happens if our trusty switchboard operator is walking down the street, slips, and accidentally drops the only master key to your entire protocol right down a storm drain? Because, in Web3, there is absolutely no forgot password link to click. If the private key controlling that single owner address is compromised or permanently lost, well, you are in serious trouble.
Let's look at the 2 absolute nightmare scenarios here. First, a lost key. The key is just gone forever. This means your contract is practically bricked from an administrative standpoint. You can never upgrade it, you can't pause it during a flash loan attack, you can never adjust the fees again. But then there's scenario 2, a stolen key. And this is arguably way worse, because now an attacker holds your master key. They can instantly reconfigure your decentralized application, they could drain funds if the contract allows it, or just completely destroy your services for fun. The big takeaway? One compromised key equals full, unilateral administrative control.
Okay, Section 4, the ownership lifecycle. Let's talk about temporal authority.
See, just because an address is the owner during deployment doesn't mean it has to hold the key forever. Think of the owner like a highly paid IT consultant.
During the initializing phase, the consultant, meaning the deployer, has permanent ownership just to set all the parameters up. Then we hit the transitioning phase. Here, the consultant uses transfer ownership to hand the keys off to a board of directors, which in Web3 terms is usually a governance contract or a multisig, and then they ride off into the sunset. Or we go straight to the finalizing phase, ephemeral ownership. The consultant sets the machine running, makes sure it's absolutely perfect, and then throws the key into a digital volcano by renouncing ownership entirely. This sets the owner to the zero address and makes the contract a fully immutable piece of public infrastructure.
Let's ground this theory in a practical, real-world example, right? Imagine you're building a DEX, a decentralized exchange. What exactly is this owner capable of doing before they walk away? Well, they might have control over emergency actions like pause, which literally halts all trading if a bug is found. They might control tuning actions like set fee basis points to tweak the economics of the exchange on the fly. Or most powerfully, they might have an upgrade function, allowing them to swap out the entire logic of the contract overnight. These are God mode powers. And that's exactly why deciding when to transfer or renounce that power is quite literally the most important architectural decision you are going to make.
And that flows perfectly into Section 5, Real-World Tradeoffs. Choosing your model.
So, the ownable pattern gives you incredibly fast iteration. The code is dead simple, and the operational overhead is basically zero, because one person just clicks confirm in their wallet. It's a fantastic tool for early-stage startups or non-critical systems. Conversely, a multisig or role-based architecture requires actual human coordination and a much more complex setup. But honestly, if you are handling millions of dollars in a low-trust environment, that friction is a feature, not a bug. Distributed control is mandatory for critical money handling.
Now, this leads us to a massive, non-negotiable best practice. You must always document your intended owner lifecycle in the contract's README file. If I'm an auditor or user thinking about trusting your new protocol with my hard-earned money, I need to know your game plan. Are you keeping the key forever? Are you planning to transfer it to a DAO in 6 months? Or are you going to renounce ownership the very second the token sale is over? By explicitly stating your intentions, you prevent auditor confusion, you stop community panic, and you build real trust. Never leave your users guessing about who's holding the switchboard operator's keys.
All right, we made it to Section 6, wrapping up and next steps, where we get ready to build this machine. Before you open up your editor and start typing out code, I really need you to remember these 3 core takeaways. Number 1, the ownable pattern provides a super compact, easily auditable way to enforce single address authority. Number 2, it drastically simplifies administration, sure, but you must accept that it centralizes massive risk into one single private key. And number 3, your ownership lifecycle choices, whether you hold, transfer, or renounce the key, will ultimately dictate the long-term upgradability and the true decentralization of your protocol. So I'm going to leave you with this final provocative question. As you move on to the next lesson and prepare to write your constructor, who will you trust with the master key? Is it yourself, a governance board, or nobody at all? Thank you so much for joining me today for this explainer. As always, I want to encourage you to visit ForgeBot College to dive deeper into this subject, grab the code snippets for our next lesson, and explore tons of other amazing Web3 content. So, on behalf of Forge College, keep building, keep learning, and I will see you in the next one.